to make an announcement, and that is that there's going to be a special issue of Catalysis today from this symposium called Syngas Creation and Its Use. And the organizers, Bertrand Davies and the undersigned, would like to have your contributions before or in the beginning of June at the latest. Thank you very much. Session. And the first talk will be given on nickel oxide-based oxygen transfer, OTM materials, right? And please.
Good afternoon, ladies and gentlemen. I would like first to thank the organizers for inviting us to participate in this honoring event for Rostrup Initiative, whose contributions to science and technology inspired all of us for many years, working with production of hydrogen. This is a work collaboration of the Rostrup University in Greece and the Texas A&M University in Calcutta. This is the outline of my presentation. I will start with a brief introduction, actually introducing a new concept, the concept of sorption enhanced combined with chemical looping methane reforming. I will continue with the thermodynamic analysis of this complex concept. Then I will switch to the experimental work and present the development we have done on oxygen transfer materials based on nickel. Then I will talk about preliminary testing together of the oxygen transfer materials and CO2 sorbents in the sorption enhanced chemical looping reforming, and I will end my presentation with the conclusions. I will skip this slide because everybody knows the importance of hydrogen production, and nowadays the process which is mainly used for the production of hydrogen from methane is the conventional steam methane reforming, which is a process, a highly intensive process, multi-step process, because we need to purify hydrogen, and this has high cost. Recently, an effort has been directed towards finding alternative processes which can produce hydrogen in one step, in a single step. And this process, the sorption enhanced steam methane reforming, has the advantage that it produces hydrogen, it purifies hydrogen, because in the reformer there is calcium oxide, or a material which can remove continuously the carbon dioxide. So we can have hydrogen coming off the reformer at very high purity, over 90%. The problem with this process is that we need to regenerate the calcium carbonate, and for this we need energy. While the carbonation of calcium oxide in the reformer provides the necessary energy, so this reformer operates almost thermally, we need the energy for this step. So, going one step further, one might ask, how could I get some energy in situ for this reactor, for the regeneration reactor? And the answer is by having combination between the sorption enhanced and the chemical looping reform. By this concept, we can have nearly autothermal operation both in the reformer and in the regenerator. How? By having inside the reformer an oxygen transfer material, reducing this material, and then by oxidizing this nickel, in our case, nickel oxide, we could provide directly the energy we need to reactivate the solvent. Let's have a closer look to the main reactions which take place in these reactors. The reforming reactor, we have first the steam reforming reaction, the water acid. These two reactions sum up with this one. And if we have calcium oxide in the reformer, then we can continuously remove CO2. By removing CO2, we shift the equilibrium to the right, so we can increase the purity of hydrogen, and of course we can increase the conversion of methane. This reaction is highly exothermic and it couples very nicely with the endothermic steam reforming. By having combination with chemical looping, this means that we will add in the reformer nickel oxide. Part of methane will react with nickel oxide, will reduce nickel oxide, so nickel actually will serve then as a catalyst for the reforming. Methane can react with nickel oxide to produce also CO and these two can also reduce some of nickel oxide. So these are the main reactions that take place in the reforming reactor, while in the regeneration reactor we will have the solvent regeneration, which means a calcination reaction by which calcium carbonate is converted to calcium oxide and CO2. And of course, the reactions which provides the necessary energy for this calcination reaction is nickel reoxidase. So nickel plus oxygen give us nickel oxide. Since all of these reactions are reactions which are affected by equilibrium, our first step in our research was to perform a thermodynamic analysis and define the optimum operating conditions and the energy balance. So for this we investigated several scenarios like the conventional steam with methane reforming, the simple sorption-enhanced reforming with calcium oxide-based solvent, and the sorption-enhanced chemical looping together with sorption-enhanced together with chemical looping, using nickel oxide as an oxygen transfer material. We investigate the effect of several parameters like temperature, pressure, steam to carbon, calcium oxide to nickel oxide ratio, calcium oxide to methane ratio, for the reforming and the reoxidation steps. We did all the calculations by using the software by Aspen Plus 20, and of course we developed the necessary flow diagrams in quite a large detail in order to get reliable energy balances. I'm not going to explain everything, all the results we got from this thermodynamic analysis. I would like just to show you what is the effect of the most important parameters, like the effect of ratio of calcium oxide to methane ratio. In these graphs, I'm presenting the reformer performance. In other words, the methane conversion, the CO2 capture, hydrogen yield, and hydrogen purity as a function of calcium to methane ratio. With the red symbols, we represent the data for the combined sorption-enhanced and chemical looping. With the black symbols, the sorption-enhanced. As expected, by increasing the calcium oxide ratio, we increase the CO2 capture and hydrogen purity. At values higher than 0.8, we don't see any further effect, and this is due actually to the thermodynamic equilibrium of calcium carbonate to calcium oxide. Keep in mind that this data were taken at 650 degrees centigrade, and this is the temperature, the maximum temperature in which we can get advantage of using the calcium oxide in the reformer. If we have higher temperature, then the equilibrium of calcium oxide and calcium carbonate is in this sign. So we need to operate at lower temperatures. As we see here, hydrogen yield increases with the increase of calcium oxide to methane ratio. Mostly for the sorption-enhanced reforming, we have a loss in hydrogen yield in the case we have the combination of chemical looping and sorption-enhanced. By this data, we can define the optimum operating window for the ratio between calcium oxide and methane. We should work in the area between 0.8 and 1. If we see the heat duty, as expected, the more calcium oxide we add to the reformer, the lower is the heat duty in the reformer. And we can achieve 80% lower heat demand when we use a ratio of calcium oxide to methane 0.8. And this for 650 degrees centigrade. We didn't observe any differences, and practically the presence of nickel oxide in the reformer does not affect the heat duty. However, when our heat balance includes also the regenerator, then we see that the picture changes. And we can see that in the case of sorption enhanced, we have a decrease in the heat duty, but not that much. When we combine it with the presence of nickel oxide at a ratio of nickel oxide to calcium oxide 0.5, then we can achieve 26 less heat. We can have a conservation about 26% in the heat demand in the system of the reformer and regenerator. And this is due to the oxidation of metallic nickel oxide. What about the effect of nickel oxide to calcium oxide? If we see this graph, then we can see that hydrogen purity slightly increases, or very little increase in hydrogen, over 92 to almost 70%, when nickel oxide to calcium oxide ratio is 1:1. So in order to compensate for the loss in hydrogen yield, we need to operate at a window of 0.5 to 0.7. Let's now compare the three processes. And in order to have meaningful comparison between the three processes, we need to compare the processes under optimized conditions for each process and assume, of course, similar product quality. This means that the comparison was made for steam methane reforming at 850, operating at 850 and 25 atmospheres, steam to carbon free. For the sorption enhanced reforming, 650 temperature in the reformer, 850 in the regenerator, similar temperatures in the combined sorption enhanced chemical looping. And we had to add some more additional steps. We added the compression of hydrogen at 25 atmospheres, also for these two processes, in order to have similar quality of hydrogen, and we need to have hydrogen at high pressure. And we had to add for the steam reforming process, the rectisol process, in order to capture CO2 and increase the purity of hydrogen. By this, we can see that the hydrogen yield which is achieved varies between 80 and 90%, with the steam reforming showing the lowest hydrogen yield and the sorption enhanced the highest. Going to hydrogen purity, by introducing the rectisol process, we were able to increase the hydrogen purity to 94% in the similar range that the hydrogen purity which we produce, we can achieve from the sorption enhanced and the novel process of sorption enhanced and chemical looping. What about the thermal demands? The thermal demands for the steam methane reforming amount to 100 megajoule per kilomole of hydrogen, while by having this concept, this novel concept, we can decrease actually the energy demands by 55% than the conventional process for the same hydrogen quality. Pressure of 35 bars and purity almost 94%. But all these are theoretical data, and we wanted to know how the system, this concept, behaves in reality. So for this, the key point is to develop materials. Materials as oxygen transfer and materials as CO2 sorbents. And these materials should to fulfill several requirements. They have to show high capacity, the materials for CO2 sorption capacity and high oxygen transfer capacity. They have to be hydrothermally stable. They should show fast kinetics compatible with that of reforming, and especially for the oxygen transfer material, the materials should exhibit actually high catalytic activity, because the oxygen transfer material will serve also as catalyst for the steam methane reforming. We selected nickel oxide as the oxygen transfer material, and the reason is that nickel oxide has high capacity in oxygen transfer, which is the highest among all the oxygen transfer materials which are known from the literature for the chemical looping. And these are either iron or copper or manganese oxides. The nickel oxide shows the highest oxygen transfer capacity, and it has very high catalytic activity in reforming. I'm not going to present you the work we have done for the development of calcium oxide CO2 solvents. I will stick only to the development of oxygen transfer materials. Our partners in Qatar synthesized 4 different oxygen transfer materials containing 48% of nickel oxide on supports like alumina, silica, titanium, and zirconia. We measured the DED surface area, and we found that this depends, of course, on the support use. The higher is the support surface area, the higher is the oxygen transfer material surface area. We characterized these materials by X-ray diffraction, and we found, as expected, due to the very high loading in nickel oxide, that the main crystal phase is this of nickel oxide. For the nickel on silica and nickel on zirconia, we didn't observe any interaction between the support and nickel. However, we did observe nickel in this sample, 40% nickel on titanium, and also nickel aluminate in the sample which was prepared, which was supported on aluminum. By using this data, we calculated the nickel oxide crystallite size, and we found that, of course, due to the very high loading, the crystallites are big enough, and the size of the crystallites depend also on the surface area of the support. The crystallite size varies between 30 and 60 nanometers. As these are considered as reducible oxide, we would like to know about the reducibility of the 4 materials, and for this we performed hydrogen PTR. You see here the profiles we got, and there are for which we can see similarities and differences, but what is in common for the 4 materials is that all OTMs exhibited peaks, reduction peaks between 300 and 500. For the case of nickel and titanium, we observe a peak at higher temperature, and this is due to the reduction of the nickel titanate, while in the nickel and alumina, we observe this high temperature peak, which was ascribed to the reduction of nickel aluminate. So once we had characterized our materials, we tested the materials in the flow unit, as first of all to check about the pure reforming activity, as happens. So we pre-reduced the material at 650 degrees centigrade, and then we started the reaction by having a feed of methane and steam at the ratio of 3, reaction temperature 650 for very high space velocity. Here you see the results we got, methane conversion as a function of time. 2 of the 4 materials behave quite satisfactory. The nickel and alumina, very high conversion. Nickel and zirconia, high conversion. And the deactivation was lower than 10% after 10 hours of testing. However, nickel and silica and nickel titanium, they were disappointing. In order to check if the reason for such a high deactivation was the very high gas-hour phase velocity, we performed another series of tests with these 2 materials at lower gas-hour phase velocity, and again the same picture, the same very fast deactivation and low methane conversion was obtained for nickel and silica and nickel on titanium. So we then wanted to know what was the reason that these 2 materials did not give us high methane conversion and deactivating so fast. So the first question is there any carbon on these materials? So to answer this question, we did temperature programmed oxidation, and here you see the profiles of CO2 for the 4 materials. As expected, the profiles are different both qualitatively, different types of coke on silica and titanium, while coke over nickel and zirconia oxidizes at higher temperature. When we calculated the amount of carbon, we found that it's very, very low. And since the duration of each test was different, then we calculated again the rate of carbon production based on organized or calculated as mole of solid carbon per mole of methane that was admitted in the reactor. Again, the two very bad materials, very bad catalysts, show high rate of solid carbon formation, but again this rate is very, very low. So carbon is not the reason. We measured the crystalline size of the used catalyst for silica and titanium. We found that there is some sintering. The crystallines become bigger, but again, this increase cannot explain the very high degree of deactivation. We did XPS analysis for the nickel and titanium, and we found that indeed, in the used catalyst, the intensity of the peak, which corresponds to metallic nickel, lowers very much. So actually, in the presence of titanium, this oxygen transfer material, this catalyst, nickel is oxidized by steam at the relatively low temperature of reforming. The case for our best catalyst, best oxygen transfer material, is different. This is a stable material, and for this we found that in the used catalyst, actually, the amount of metallic nickel is very high. So zirconia can stabilize nickel in a reduced form even in the presence of steam at 650 degrees centigrade, while titanium does not. So this was probably the reason. For silica, we haven't done yet the XPS analysis, but silica, we know that in the presence of steam is not stable, so it was rather expected that nickel or silica will not be the best catalyst. So our next step was to check the materials as chemical looping, as oxygen transfer material. And for this, we selected only the promising materials, the nickel and aluminum and nickel and zirconia, and we introduced them in the reactor without any pre-reduction, in oxidic form. We did the test for 1 hour under reforming condition, and then we switched and increased the temperature at 850, and we oxidized the material. Let's see how the reforming proceeds. We have an oxygen transfer material which is in oxidized form, and it seems that very, very easily and very fast nickel oxide is reduced by methane, and then the catalyst which is formed drives all the reforming reactions. The methane conversion is high in the presence of nickel and aluminum. The methane conversion is very high in the presence of nickel and zirconia. So both materials are active when used as in oxidic form. Of interest to see that in the oxidation part, in the oxidation step, we didn't see any CO2, any carbon dioxide, which means that there is not any coke formed during the reforming period. Here you see the 20 cycles for this chemical looping, reforming and oxidation activity of nickel and zirconia. By these blue dots, we present the hydrogen concentration. This is the reformed gas concentration. These black data are the methane concentration. As you see, we have almost constant gas composition during the cycling of reforming and reoxidation. Total duration 20 hours. And we observe the activation degree of almost only 2%. The lower the activation degree compared to the pure steam reforming might be ascribed to the oxidative treatment at 850, which may regenerate the catalyst and keeping the active metal area constant. With aluminum we did the same, and here I'm presenting the results as methane conversion as a function of cycling. However, compared to zirconia, alumina didn't show satisfactory performance, and The most probable reason for the instability of alumina, of nickel on alumina, under this cycling is the lower hydrothermal stability of this support. Now let's see some very recent results in which we combine actually this oxygen transfer material, the nickel of zirconia, which showed very promising performance, with the CO2 sorbent. And the CO2 sorbent is a sorbent which is a mixture between calcium oxide and zirconia. Actually, we had done a lot of work with these sorbents, and we found that this sorbent, which by chance contains zirconia also, shows a stability for over 100 cycles as a sorbent of CO2. So we mixed these two materials at a ratio, molar ratio 0.5 to 1, and we tested under reduction reforming carbonation conditions at 650 degrees centigrade for steel to carbon ratio 4. And then for the oxidation at 800 in airflow for 10 minutes. Here you see the results we got. In this graph, I'm presenting the hydrogen concentration of the reactor exit as a function of time. For this period, for almost 50 minutes, the mixture of the sorbent and the oxygen transfer material worked perfectly. Why? Because we saw very quickly the production of hydrogen. The methane concentration shown in this axis is very low, almost complete methane conversion. And the CO2 sorbent captures continuously the CO2, which has a very low concentration, and the CO concentration is very low. So we produce a pure, not 100%, 95% hydrogen is produced for 15 minutes. Once the sorbent starts saturating, then after 15 minutes, then we go to the breakthrough period, where we saw the increase in methane concentration, lowering of the conversion, and the increase of CO and CO2. After almost 70 minutes, then the system behaved like in steam reforming, in conventional steam reforming. The hydrogen purity decreases and the CO and CO2 concentration increases. So indeed, the sorbent and the oxygen transfer material work together, producing hydrogen. But what about the oxidation step? Once we finish with this step, then at 650 degrees centigrade after helium purging, we started the flow of air. And then what we saw very soon after the air ignition, we observed that the temperature increased. It was around over 800 degrees centigrade, and at the same time, in the CO2 analyzer, we saw the CO2 coming off the calcium carbonate, and at this point, we started the external heating. So by some simple calculations, we were able to see that actually the preheating thermal demands and more than 35% of the heat duty of the sorbent regenerations are covered by the highly exothermic nickel reoxidation. So in this step, in this area here, we have the reoxidation of nickel to nickel oxide, the production of heat, which heat is used for the increase of temperature and the calcination of calcium carbonate to calcium oxide. So indeed, the concept can be applied in practice. Of course, we need to optimize the condition, we need to do more work, and we need to do a lot of science. So coming to the conclusions, the concept of combined chemical looping and sorption enhanced steam methane reforming for the production of pure hydrogen in one step with minimum heat demands was investigated theoretically and proved experimentally. 55% lower energy demands than the conventional process for the same hydrogen quality. The oxygen transfer material which we developed, two of them showed very promising performance, and especially the nickel zirconia, almost negligible deactivation, high activity in chemical looping reforming, while the combination of two materials, one oxygen transfer and one sorbent, based on calcium oxide and based on nickel, the oxygen transfer, showed potential for this novel concept. Production of hydrogen with over 95% purity and covering a lot of the energy heat, the heat which is needed for the calcination, for the decomposition of calcium carbonate by the oxidation of nickel to nickel oxide. I would like to thank the Qatar National Research Fund and the program NPRP for funding this research, and you for your attention.
Thank you. Yes.
That's an interesting concept, and for sure your thermodynamic analysis demonstrates all this, and people have worked on this. So it's interesting whether one can find it a solution. Also, the scheme has the advantage that you create a concentrated CO2 stream. So if you have, if you talk about CO2 sequestration, these kind of systems have special interest. However, when you compare with steam reforming technology, you should compare with a modern hydrogen plant. I'm aware of companies who can guarantee the energy consumption 6 to 10% higher than the theoretical minimum. These are using low steam to carbon ratio and pressure swing adsorption. So go into the literature and see the real figures because a lot of things have happened since one made hydrogen plants with high steam to carbon ratios and CO2 wash systems. Second thing, people who have worked with fluidized bed and reforming have had big problems because the CO will react with the hydrogen on catalyst dust in downstream equipment. It has, in fact, destroyed some developments. I know Mobil worked on that. So you should be very much aware that you have no dust leaving your reactor, and you have CO, small amounts of CO leaving, and that will be lost by methanation. Third question. You have hot air leaving your calcination step. How do you recover the heat of the hot air leaving your calcination step?
How could you repeat?
You have air leaving the calcination step. You have very hot air there, right? How do you recover the heat from that?
I don't remember. I don't remember the exact flow diagram in our thermodynamic analysis, but we have done this.
But the heat balance is on the solid gas reaction, but you have a big air stream coming through your calcinator, and that air will leave at high temperatures. And so my question is, how do you recover that heat? You can't give it to the birds.
Of course, we can produce some steam.
But how do you calculate the steam in your energy balance? Hydrogen plants should be neutral in steam. You can't make a hydrogen plant as a steam generator. So I'm just saying this to warn you when you make these calculations. Okay. So it's said in a good will, because a general scheme where you have the combination of the CO2 absorption on calcium oxide coupled with the steam reforming is extremely interesting. But it's just your comparison with present technology is not ready.
So you think that the advantage is much low?
Yeah. Nobody's using rectisols in hydrogen plants.
Oh, that's 20 years.
But I think we have to stop now because...
The reason we used a rectisol was that it was almost ready from the asphalt.
Yeah, okay, I understand, but I'm just saying nobody is using it in practice today. And I'm afraid we have to move on to the next one because we have exceeded our time a little bit. So I'm sorry you have to discuss. But before you leave, I would like to make an important announcement. And that is, we have persuaded the guest of honor here to give 2 talks tomorrow. One is titled 50 Years in Catalysis, and the other one is even more interesting, I think, Lesson Learned.